Okay, welcome to this YouTube live session on quantitative skills and reasoning, and we're going to start off with investing in loans. Going to work on a few other topics including mean, median, and mode, cumulative frequency, relative frequency, all that jazz, 5-number summaries, and so on and so forth. And if you have any questions, there's a chat box over on the right hand side, most likely depending upon how your layout is. Feel free to take a look, and I'll be happy to help you out along the way. So let's get started. Our first problem. Suppose you invest $3,000 in a CD with an annual interest rate of 6% compounded monthly. Okay. Determine the amount of money you will have after 20 years. So there's a few formulas you have to distinguish between, but notice we're investing $3,000. We're just doing it once. Okay, so investing $3,000 once, and then we're talking things that are compounded monthly, right? So we're talking some compounding going on here, and we want to determine the amount of money after 20 years. And our annual interest rate, just to kind of highlight that, is 6%. So since it's a single investment, and we're talking investments, not loans here, and we're looking at compounding involved, and there's a definitive rate or time rate in terms of how often the compounding is occurring. This tells us is the compound interest formula, and the formula that we used for our class, and there's different ways to write this, but I'll help distinguish what each of these are. So you have A equals P times the quantity 1 plus R over N raised to the NT power. So first off, what does P stand for? That's our principal investment. Okay, and then we have our R value. What is that? Well, our R value is our annual interest rate. Written as a decimal. So that's a key converting portion here. Sometimes people forget to make that conversion, and so it gives them a little bit of a trip up. The N value, what does that stand for? That's the number of times compounded and then since we're talking about an annual interest rate, it's the number of times compounded per year. So for example, if you had a daily interest rate, this would be per day. How often is compounded per day? And you have to adjust accordingly. And then T stands for our time in years. And then the A value stands for the final amount. After T years. Okay, so we have actually all this information, and we're going to just plug it into a formula. That's all there is to it. So we'll start off. Suppose you invest $3,000. So we're starting off investing $3,000. It's not a final amount that we're looking for or anything like that. So that's our P value. P equals $3,000. Okay, our next bit. Annual interest rate of 6%. So that stands for our R because we're talking percentage, and we want to write it as a decimal. Well, 6% written as a decimal is 0.06. Okay. And then after that we need N. Well, how many times is it compounded per year? If we're compounding monthly, well, notice there's 12 months in a year, so that means N has to equal 12. And then the next part, T, what does that become? Well, T, notice we're talking after 20 years. So 20 years right there. So we have P, we have R, we have N, we have T. It looks like we can find A. And what we can do is just plug them all into the formula. So A equals 3,000. And then we have 1 plus, what's R? It's 0.06 divided by 12 raised to the 12. And then our T value is 20. Now we need to punch this into the calculator. What do we do here? What I would suggest is actually doing what's inside the parentheses first, and then you can also figure out what this value is, right? So it might be easier. We'll have 3,000 and I'll put 1 plus. We'll do 0.06 divided by 12, and then 12 times 20, notice you can just multiply 12 and 2 is 24, and then you add the extra 0 there, so that's going to be 240. And so now we're kind of ready to rock and roll here. So you get 1 plus 0.06 divided by 12, and you raise that to the 240th power, and then we can multiply by the $3,000. You could have done it first. It just might be easier for us to work with the hardest part, the parentheses first. If you've done this correctly, you should get an answer of approximately, now I'm going to do a little bit of rounding here. I'm going to round to the nearest cent. And so $9,930.61, rounding down there. Okay. So make sure you can plug that into the calculator, and so double check your work, make sure that all that's going well. If you do have questions, I can illustrate that, but hopefully at this point you have the calculator part down. If not, just let me know. And if you have any questions along the way, once again, please just ask them in the chat box. I don't see any at this time, so we'll just keep on moving. Okay, so another one, and talk about investing in loans and how this goes. Suppose you wish to retire in 45 years with $2 million in a 401k. So if you expect an annual rate of return of 8.5%, then what regular monthly deposit should you make in order to get to $2 million after 45 years? Okay, in this one, we got to think about what's actually going on. What are we doing? Is this a loan? Is this an investment? Well, notice we're talking about depositing, right? And we want to retire with $2 million. I sure hope you don't want to retire with $2 million in debt. That wouldn't be a fun experience, would be my guess. So we got to keep that in mind. And what's happening? We're doing not just any deposit, a regular monthly deposit. So it's not just one investment anymore. So we can't use just that compound interest rate formula. So this means that we have a different formula in play. And what we're going to end up having, and we want a final amount, which is what the A stands for. But since we're making regular monthly payments, we'll put that out here with a P with a subscript M. Okay? And then up top, we're going to do a similar formula to what we had before, the 1 plus R over N raised to the NT. But then we're going to subtract 1. And then we're going to divide by this R over N. For those of you that don't know what this is our savings plan formula. Okay, so we're making savings. Some of you might have done annuity formulas and things like that, similar stuff. So maybe different symbols, so I'll kind of explain what each of these mean. So the piece of M, what's going on there? That's our regular deposit amount. What's our R value? R value, and notice it's in two places here. That's our annual interest rate. Written as a decimal. Okay, what about our N? We have N in 3 places, if you notice. That's the number of times compounded per year. Okay, what about T? So T is time. And since this was per year because of the annual interest rate, time is going to be in years. I can't fit it right there, but hopefully you get the gist. And then what is our A? It's our final amount after T years. So we have all the things in place. How do we solve this now? Well, we got to figure out what are we looking for and all that jazz. So suppose you wish to retire in 45 years with $2 million in a 401k. What does that mean? Well, that means at the end of the day, we want to finish with $2 million. So this is a little bit different. We're going to start with A equals $2 million. Okay? We want to actually finish and figure out what piece of M is, and the way we can tell that is notice what regular monthly deposit should you make in order to have this. So that's what we're looking for at the end. So now after we have A, we can get R. 8.5% is our annual rate of return. So we can put this in as 0.085. Just an FYI, usually the S&P 500, which is a measure of around 500 stocks, is around a 7% return over time, long periods of time. So you can kind of anticipate this is a little bit on the high end here, but a return nonetheless. N, so in this case, notice N, we're talking a regular monthly deposit. So how many times we're going to be compounding? We'll talk 12 times per year. T, what is T? How many years? Well, notice it says 45 years until we retire, so 45 working years. And usually you're talking 40 to 45 working years for a lot of people. Not everybody, but a lot of people do have 40 to 45 good working years in them. Okay, so now we have all our numbers that we need, and we want to plug that into our formula here. So we have A is 2 million. So we'll put in that 2 million. Equals piece of M, we have no idea what that is just yet. Well, if you do, let me know. That's always good to know as well, but hopefully we'll do the work to get there. So you have this 1 plus R is 0.085 divided by N is 12, and you have a 12 up here, and then the T is 45 years, and then minus 1 all divided by, then we have R is 0.085 and divided by our 12 right here, and now it's just plug and chug time. But what's going to happen at the end of the day? All of this stuff right here that we just put in brackets, that's going to be just some number. And if we want to solve for P of M, what do we need to do? Well, we need to try and take this number times P of M and get what P of M is. So the ways to do that is to divide both sides by whatever this number is. So what we find is P of M, or P subscript M I should say, is equal to 2 million divided by all that junk that we just wrote, right? So you have that 1 plus, don't let your eyes fool you, that's a perfect plus, 0.085 divided by 12 raised to the 12, and then a 45 right here, and then we had a minus 1, and all that is divided by 0.085 divided by 12. So notice we have some form, and we'll have to do some work on a calculator, but we can figure out what the answer is. Little tricks of the trade. What I would do is figure out what this bottom part is, so what that part is. Find this first on the calculator, and you can write it as a decimal if need be and try and solve it from there. Make sure though you're putting your numerator in parentheses in this piece, and then you divide by the denominator in parentheses. That's actually a common error that most people make, so just keep that in mind. So 1 plus, you have 0.085 divided by 12, and then make sure your exponent, you could already multiply out 12 times 45 if need be, and then you have it in there. It's easier to plug in. But take that and then subtract 1. Make sure to put that whole numerator in parentheses. Divide it by the 0.085 divided by 12, and after that you'll have some number, and we want to take 2 million, so just make sure you get the 2 million, the right number of zeros. We'll have 6 zeros if you've done that correctly, and divide that by our answer. And this is what can surprise people. People talk about being multimillionaires and stuff like that. If you give yourself that amount of time, this might sound like a lot of money at first, but it only takes $320.38 every month in order to build to 2 million in 45 years, given that rate of return. Granted, that rate of return is slightly higher, but when you think about it, what are we putting in? So you can multiply this by 12. So if you take your 320.38 times 12, notice you've put in $3,844.56, right, every year. Think about that. You're putting that in every year, yet you're getting out 2 million at the end of the day. So you didn't even put in close to that amount, and you're getting quite the return, right? You put her in around 173,000, but it pops out that beautiful 2 million amount. So keep that in mind when you're doing this stuff. Keep investing and doing things and do it consistently. It helps out in the long run. That's the power of compound interest. I can't emphasize that enough. Compounding things over time. So hopefully that makes sense of how to use the savings plan formula. And what we're going to do now is try and look at another problem. And this is more another real life scenario. Suppose you find a $200,000 home that you wish to purchase. You have enough money to make a 20% down payment, but you will need to take out a mortgage to finance the rest of the purchase. You can choose between a 30-year fixed mortgage with an annual interest rate of 4.15% and a 15-year mortgage with an annual interest rate of 3.85%. Determine the best option for your mortgage. This will actually depend upon your view on things, what you're looking for. But we're going to try and weigh our options. And first off, if you have a $200,000 home, before we even talk about what the mortgage amounts, like monthly payment and stuff like this is, but notice we need to take out a mortgage. That's a loan. So this type of problem is a loan problem. Don't let your eyes fool you. That's the word loan right there. So with that in mind, we're going to need a loan payment formula. And so the loan payment formula a little bit different, because what we're trying to solve for usually in a loan payment formula is the regular payment amount, so whether that's monthly or whatnot. And with these being the mortgages are usually on a monthly payment, so you can keep that in mind. So we'll go through the calculation as to what happens here. So you get P of M equals P times, you'll have this R over N up top. That probably looks familiar. And then it almost looks like the opposite, but there's some slight variations as to what we just did. So you get 1 plus R over N raised to the negative NT. So this probably looks really familiar in terms of that savings plan formula. The differences, so where the P appears and all that jazz. So P of M, that's the regular loan payment, and that's usually monthly, right? And in the case of mortgage, it definitely is monthly. But car loans usually paying something every month, so you'll have an idea as to how often you need to make those payments. P, what does that stand for? That's the initial loan amount in this case. So how much money are we taking out? R, what does that stand for? That's the annual interest rate. And hopefully we remember this is as a decimal. N is number of times compounded per year. Most oftentimes it's monthly. I have seen some things though they do daily, so you got to be careful with those. T is time in years. Okay, and then we have this extra bit. We want to make a 20% down payment. What does that mean? Well, that means you're going to pay for part of the home up front, and usually that gets rid of like private mortgage insurance and things like that. If you don't make 20% down, you're going to usually pay some extra fees along the way, and they'll just lump it into your monthly payment whether you realize it or not. And by the way, there are some other things that do pop up when you're making mortgages. Some banks require an escrow account, things of that nature. So, but this is just going to be the principal and interest paid is what we're focusing on here. So keep that in mind. You might have some numbers that vary, but the reason why is usually an escrow or some private mortgage insurance or things of that nature. This is just principal and interest is all we're looking at right now. Okay, so in our first scenario here, we got to figure out what the 20% down payment is. 20% down payment. How do we figure that out? Well, you're going to put 0.2 times the 200,000, and notice that equals 40,000. So that tells us right there something. it tells us how much we're going to take out for the loan. So P, in our case, has to equal, well, we start with 200,000, and then we're already going to pay 40,000 up front. So that means our P equals 160,000. Okay, so now we're ready to tackle these two problems. We'll start with the 30-year fixed. So we have P is 160,000 regardless. We need some other things. We need R, N, and T. So notice the 30-year, it tells you right out the gate what T is. So T is going to be, we're going to do this kind of backwards. T is 30 years. As I mentioned, number of times compounded per year, you're talking a monthly payment, so this is going to be 12 times per year. Even though it doesn't say it, this is how mortgages work, monthly payments. R value, what does that equal? Well, notice this 0.0415, right, because you have the 4.15% on that. Notice that's actually higher than the 15-year, and from a bank's perspective, that makes more sense. You want to have a higher interest rate because of a longer period of time. It means more risk for someone to borrow something for that long. So that's why you have these higher interest rates usually when you have a 30-year versus a 15-year mortgage. So keep those in mind in your calculations. So for the 30-year fixed, we got to plug into our formula. So PM equals, well, we have P is 160,000. Okay. And then we have R over N, so that's the 0.0415 divided by our number of times compounded per year, so 12. And then we go 1 minus, we have 1 plus 0.0415 divided by 12. Now notice though, the formula has negative NT, don't forget that negative. So this is negative 12, and then 30-year mortgage, so that's 30 years right there. And then we can close that thing off. Okay, so looking at this, what happens? Well, we can plug this into our calculator. I'd suggest using starting with this harder part right here where we have the 0.0415 and all that jazz. Remember, just have your numerator and denominator in parentheses. That's always pretty important there, and it's probably the most forgotten thing too. So raising all that to the negative 12 times 30th power and going there. So now we got 0.0415 divided by 12, and we have that on the numerator, and that's dividing by our denominator. So multiply all that by 160,000, and we get a monthly payment of $777.77. Okay, so that's our monthly payment. Alright, so let's take a look at the other side of things. We have that being our monthly payment. What else do we have? Well, if we do a 15-year, okay, we're talking a fixed interest rate, our P is still going to be 160,000 regardless. So now though, our T equals 15 years. Okay. Our N is still going to be 12 because it's 12 times per year because we're talking monthly payment. Our R has reduced a bit, so we have 0.0385. Okay, and then now we can plug it into our formula. P sub M equals, so this is our monthly payment. Once again, we have the 160,000. You have 0.0385 divided by 12 all over 1 minus, and I'll put that in parentheses up top, 1 minus 1 plus 0.0385 divided by 12 raised to the negative 12 and then 15 now. That makes a bit of a difference. That's a 15 there, don't let your eyes fool you. And we have that negative symbol as well. Okay. So now, what does this come out to be? Remember, this is going to be our monthly payment. So you got to get out the calculator again, plug in, chug once more. So 1 plus got 0.0385 down in the denominator. Actually, that's usually what I work with, to be honest with you. I work with this harder part where you have the parentheses going on there, and raise it to the power. That's the first thing I do, to be honest with you. It's just a lot easier to have those values in there right out the gate and then work on the rest. Not saying you have to do it that way. As I said, if not, just make sure you're putting parentheses in an appropriate place and you should be in pretty good shape. So have the whole denominator. The whole denominator, if you're actually checking along the way, the whole denominator comes 0.4381810143 if you're looking for that. And then you can plug in the numerator, 0.0385 divided by 12 and divided by that answer. Multiply that by 160,000. And so now this becomes, so you might be wondering what's going on here. This is $1,171.51. You might be saying, what the heck? A 30 year is so much better. Not so fast. Let's figure out our total loan amount. So our total loan amount, total cost of the loan. Notice we're paying that every month, right? So this is per 1 month. And notice there's 12 months per 1 year. And for this loan, for the 30-year fixed, and we'll figure out the other one here in a second. So for the 30-year fixed, what you're looking at is 30 years per one loan. So how much are we paying for the total amount of the loan? So you take that 777.77, multiply by 12, and multiply that by 30, and you might be surprised to see that your originally $200,000 home cost you $279,997.20. So basically, just that mortgage cost you an extra almost $80,000 essentially. So $79,997.20 extra just to take out that mortgage. So in the other case though, let's check out what happens here. So we have a total loan amount. Well, what do we have? We have $1,171.51, and by the way, this was dollars, so this is dollars per loan. So this is dollars per month. Once again, 12 months out of the year. Not saying you have to write it this way, but it's just one way to kind of keep track nicely. And after that, though, this is only a 15-year loan, so there's 15 years per the one loan. And so what happens here? Well, we have 1,171.51 times 12 times 15, and notice this is a lot cheaper. You get $210,871.80. Okay, so in this case, the 15-year only costs you $10,871 versus the other one costs you $80,000. So keep that in mind when you're actually going for a mortgage. How much is this thing actually costing you? It makes a big difference, and depending upon the interest rate too, but usually I have that lower interest rate with the shorter time period. Now, why would someone take a 30-year? Well, as you saw, the monthly payment is going to be lower. So some people feel like they can't afford that higher monthly payment, and you can understand in terms of which one's better. So this is open to interpretation. Personally, what do I prefer? I prefer a 15-year. Right? And why is that? Well, that shorter time period, notice I'm only paying $10,871.80 in interest. Okay? So hopefully that makes a little more sense as to how these mortgages work. Car loans, same way. The longer you stretch it out, the more you're going to pay. Usually a higher interest rate along with that longer time period too. So keep that in mind when you're doing that stuff, whenever you're taking out any loan. So, all right, let's move forward to a different topic now. So mean, median, and mode. What are we getting to here? So we have a recent poll of 400 people at a shopping mall found that the number of credit cards each person had with them appears in the table below. Determine the mean, median, and mode for the number of credit cards according to the given table. So what does this mean? What's actually going on here? Well, so most people will start to either sum up the people or sum up the credit cards and try and calculate it that way. Well, think about what your data values are. These are people, and each of them have some number of credit cards. We're looking for mean, median, mode for the number of credit cards. So for example, what's actually happening is you have 0 for the first person, you have 0 for the second person. You have a list of all sorts of people. How many, in fact? Well, we can say there's 60 people with zeros. Okay? In a similar manner, you have 1, then 1, then 1, and so on and so forth, and finishing with a 1. There's 140 ones appearing in our list. Okay? And this is more realistic as to how these data sets look. And similarly, we can do 2s, so on and so forth, all the way up to here. And notice there is 122s. And then 3s, 3, and I'll put a dot, dot, dot. These numbers are too large for me to handle writing out in a decent time frame. So 120 people, here's 40 people. So the 4s are 30 people. So, and by the way, the dot, dot, dot means we're just getting to that number of people in between, with all 3s here, all 4s here, all 2s here, so on and so forth. I can write out the 5s and 6s. So 5, 1, 2, 3, 4, 5, and then 1, 2, 3, 4, 5 of the 6s. That's what your data set looks like. Now, obviously I couldn't fill it up on this page and do all that, but if we're finding mean, median, and mode, there is an easiest thing to look at, and that's mode in this case. The mode is just the most frequently occurring. So notice there's 140 of these ones. So the mode equals 1 because there's 140 ones appearing in our list. Okay, so that part's easy. The next part, what we'll look at, we'll kind of go backwards, I guess. So we'll do the median. Now the median, the tricky part here with such a large list, we need to find the location. And the location of the median is equal to this n plus 1 over 2. And what is n? Well, n is the number of individuals or observations or whatever's going on, depending upon how your data set's collected, but the number of individuals where we're collecting the data from. So notice you can sum up all these numbers right here, 60 plus 140 plus 120. So there's 400 people, and an easier way to see that is we had it right out the gate, right? So in this case, our location of our median, it's going to equal 400 plus 1 divided by 2. Well, that's 401 divided by 2, and so notice that's going to be 200.5. Ooh. So where does that occur? Well, notice you have 60 people here and 140 people here, and I'm going to point in particular to that position right there. That position is the 200th position. And that means if that's the 200th position, that means this has to be the 201st position. Okay, so with that in mind, you have 200.5 is basically halfway in between those two. So what do? Well, the median, we take those two numbers and we average them. So you take 1 plus 2 and you divide by 2. So notice that's equal to 1.5. And we have our answer. There's our median, 1.5. And that's a lot different than what a lot of people do, is they just count up these numbers and try and find the middle term. It's not the way it goes, because you have each individual has a different number of credit cards and you have to account for that. Now the mean, right, so which I'll, and by the way, you might see a capital M up here every now and then for that. So going on the next one, the mean, we can have X bar is the symbol for that, or I'll just write mean for right now, for those of you that aren't familiar. But please get in the habit of using things like that, X bar. There's a way that we could do it. Now I could sum up everything individually, but luckily we learned back in elementary school, if I have 60 zeros added up, I can write that as 0 times 60. Okay, same thing with ones. If I have 140 of those, so 1 times 140 plus 2 times 120 plus, what is it, 3 times 40 plus 4 times 30 plus 5 times 5 and plus 5 times, or let me write this 6 first just to be consistent. 6 times 5. Okay? And all that's divided by, well, how many individuals do we have here? Well, we have 400 individuals. So, and you can see that from the 60, the 140, 120, so on and so forth. You get those numbers. So you can work this out in multiple ways, but just making sure you have the numerator in parentheses, you can do the 140 plus 240. Well, the reason I didn't say 0, first off, adding 0 isn't going to change much. Plus 120 plus, what is it, another 120 plus 25 plus 30. And so we take that answer and divide by 400. And so notice our mean is actually 1.6875. So a majority of the cards are closer to between this 1 and 2. And that makes sense because you have 200 just at 0 or 1 in that case. So 1.6875 happens to be our mean. Okay, hopefully that clears up that question. I know a few of you had some questions on that one, so and hopefully that clears the air on how you work some things like that. Alright, so let's get into standard deviation. What is standard deviation talking about? Well, you have the mean. That's a measure of center. So is the median. The median is actually the dead center location-wise. The mean is another way, it's average, and another way we measure the center of a distribution. Standard deviation, what's that doing? It's measuring how we spread from our center. And so the standard deviation formula, what you're actually looking at is something that involves the mean, but not just the mean. It's also the nice part here is we're talking about the mean squared essentially, and we're gonna have to take a square root after all said and done, I should say. And so the one that we usually deal with, there's two different formulas. There's one for a population, there's one for a sample, but the one we're usually dealing with is a sample. So we'll kind of keep that in mind. And what I'll do is I'll make a chart, and hopefully that can kind of help. So let's create an easier one and then a harder one in terms of our distribution. So we'll do our mean, let's have it be 5. The first distribution, just for time's sake, I'll only use 4 numbers. We'll do 5, 5, 5. So 5, 5, 5, 5. So now on our next distribution, let's do, well, 5's the center. We'll put, well, actually let's do something slightly different. So notice if we're having only 4 terms and we want it to be 5, I need the sum to be 20. So in that case, just we can kind of add them up accordingly. 1, 4, and let's do 7 and 9. Okay. So notice, let's call this the, I don't want to call it the X's. Let's call this group A, and let's call this group B. This way we can distinguish. Well, notice this is just 5 plus 5 plus 5 plus 5, and divide that by 4, and so we'll get 5 as our answer. Surprise, surprise, right? But for the mean for the B's, it might not be as obvious, but if we add 1 plus 4, that's 5. Whoops, I wrote 9 there. 1 at 8. 1 plus 4 plus, so this is 12 plus another 8 makes 20, divided by 4, and so that should equal 5 as well. Alright, so now notice this one seems like there's no spread whatsoever, and this one seems like there's a little bit of spread. So how do we calculate the standard deviation? Well, what I'd recommend would be to first figure out the sum of all the squares. And when I'm saying the sum of all the squares of the differences of the means. So these will be our observations. And we'll have 5 here, 5 here, 5 here, 5 here. And then we'll go, the way we kind of write this is we write xi minus xa bar, or usually it's just x bar. But so in this case it's not going to be too hard, since this value is 5 every time. You're going to get 0, 0, 0, 0. And then what we're going to do is square that for each case. And in that case you still get 0, 0, 0, 0. And then afterwards what we're going to do is find the sum. So the sum of all these is 0. Okay, so you'll have some value here, and we're going to plug it into a fancy formula. And what that formula is, in this case you'll see the S, which is equal to the standard deviation. And just by the way, I'm going to use S sub A. So standard deviation of A what does that equal? Well, the formula goes, usually you'll see this x1 minus x, in this case is a bar squared, plus x2 minus x sub a bar squared, plus x sub 3 minus x sub a bar squared, plus x sub 4 minus x sub a bar squared. And then you divide all that by n minus 1. N stands for the number of observations. And you could change this to any, like instead of x sub a bar, you could have it be x sub b bar, and so on and so forth. And then we take the square root of all this junk. So in this case though, what do we have? We have the square root of, well, we have all these being 5, so in the top, when we looked at all these sums of all the squares, we just got 0. So 0 divided by, there was 4 observations, 4 minus 1. So that's square root of 0, which equals 0. And just an FYI, if you wanted to learn, I'm happy to teach you. You can do all this with a TI 83 or above calculator. So if you have a graphing calculator, you can do all this and it'll do all the work for you. But if not, just want you to see what's happening here at least, and so we have an idea as to what's going on. So here's our observations. In this case we have 1, 4, 7, and 8. Alright, and we'll need a little bit of room for the sum down below right there. Okay, so we have xi minus x, in this case is b bar. So notice this one has the same mean, right? So this case is also 5. But now we got to go 1 minus 5. Notice that's negative 4. So something a little bit more interesting. 4 minus 5, that would be -1. 7 minus 5, that would be 2. 8 minus 5, that would be 3. And to make it a little more interesting yet, and notice if you were to sum up all these as is, right, notice you get -5, +5, oh wait, that's back to 0. So that's why we don't just add them up straight away, and that's why we actually look at the squares of these things. The squares of these differences from the mean. So it's talking about spread away from the mean, and the way we can get to that is the squaring here. So when you square -4, notice you get 16. When you square -1, you get +1. When you square 2, you get +4. And when you square 3, you get 9. And remember, we're going to have a sum up in the numerator of our standard deviation of our b. So we got to sum all these up. So you get 17 plus another 4 is 21 plus another 9 is 30. So with that in mind, okay, we're ready for our standard deviation of b. So I'll write SB. Remember, that's the standard deviation of the set b. What do we get? Well, we get the square root of, in this case, we have 30 up top, and then we only have 4 observations once again, so this one's 4 minus 1. So that's the square root. Notice 30 divided by 3 is just 10, so that's the square root of 10. So notice the square root of 10 is just some number between 3 and 4, closer to 3 than it is to 4 if you don't have a calculator. And if you do have a calculator, just plug it in and you'll see that this is approximately, we'll go 3.162. Okay, so hopefully that lets you see how these things work in terms of finding the standard deviation. So is it possible to have 2 different data sets having the same mean and different standard deviations? Yes, and that's the whole idea, is just fiddle around data sets. And if you wanted to use different ones other than this, there's tons of examples. In fact, there's infinitely many examples. The key is just start fiddling around with the numbers, you know, seeing what happens with different data sets. And you can have all sorts of possibilities. Do I have to keep the standard deviation? Notice this was 3. Could I have the mean be 5 and say the standard deviation be 1,000,000? Yes, yeah, it's not that bad. I mean, you can just adjust accordingly. Just have your numbers be spread out as long, and you can go to negative and positive numbers, and all of a sudden you have something really nicely that cancels out and still gets you that mean of 5. So in a lot larger spread, so the standard deviation is higher. Okay, so hopefully that clears up standard deviation stuff. I'm not seeing any questions, so we'll just keep on moving. Alright, so next part, we want to find the 5-number summary of the following stem and leaf plot. Okay, so we have a stem and leaf plot. What's the 5-number summary? What the heck is that? So a 5-number summary consists of 5 magical numbers. You have the minimum, you have the first quartile, which we'll call Q1, or first quartile. You have the median, which will go by this M here, that stands for median. You have the third quartile. And you have the maximum. And then usually you list them in increasing order, and that's your 5-number summary. So minimum, what is it? Well, how the heck do we read a stem and leaf plot? Well, all this means is we didn't specify, so this would have to be tens digits, and this would have to be your ones accordingly. If we have this, so you have a 2 here and a 1 here, so that means tens is in your 20s, and then this is your 1, so that first off means your minimum is 21. And notice you can't get any number smaller than up there. So this is actually where you're going to look all the time, the top and then the first leaf up at the top on the left hand side of all the leaves. That's going to be your minimum. Your maximum, if you have a stem and leaf plot, you go down to the bottom stem and then go all the way to the right, and that should be your maximum. So notice in our case we have 79 being our maximum. Okay, so the rest of it though, we're going to need to do a little bit of work. And in order to do that, I'm going to kind of change colors here. Oops, wrong one. So let's go with blue and trying to give you a different thing is what's going on here. So the median location, so the location of the median. We need the number of observations plus 1 divided by 2. Okay, so Let's start counting. We have 3 here. There's 6, 8, 9, 12, 15, 17, 22, then that makes 25. So notice this means that we have 25 plus 1 divided by 2. So our median location should be 13. Okay, that doesn't mean that's our answer, it's just our location. So notice we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 right there. Okay? That's our median. So what number is that? 5 and then a 2, so that makes 52 is our median value. Now notice this split it into 2 different data sets, and so you should have half of them on one side of the median and half of them on the other. And so what we can do, there's a couple different methods for doing the first quartile and third quartile. We'll start with the first quartile. You could do the 25 percentile and do that calculation. That's method 1 that we talked about. And then method 2 is basically take the median of all this data here from here to here. Okay? So all those are data points. So notice how many observations are there for us to look at for the location of Q1. Well, notice you have 3, 6, 8, 9, 12. So that means we have 12 plus 1 divided by 2. So that means we have equal to 6.5. So notice you have 1, 2, 3, 4, 5, 6, and 7. So basically, I'll put a little star right here. That star is where our quartile 1 is going to occur. Halfway in between this value and this value. So what does that mean? So in order to find the Q1, what do we have? Well, we have 35 and 36 are our 2 values on our stem and leaf plot. So you take 35, add up 36 with that, and divide by 2. And notice our answer is just 35.5. Okay, on to the third quartile. What happens? Well, third quartile is going to be the same song and dance. Notice we have the same number of values, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And that's what should happen with our median. It splits them right down the middle. So we have 12, so we know it's the 6.5 position. So from here, if we're just breaking up this data set, so you go 1, 2, 3, 4, 5, 6, and there's the 7th. So luckily, these 2 numbers are the same. So that makes it easy. You can still go through the averaging just for practice. You go 63 plus 63 divided by 2, and you get your answer to be 63. So notice when we write our 5-number summary, what do we get? So 5-number summary. You just want to write them in increasing order. So we have 21, 35.5, 52, 63, and 79. Okay, so hopefully that makes sense on the 5-number summary and how that works, and finding quartiles, minimums, maximums, medians, once again, with the stem and leaf plot. Oh, and by the way, if you do have a 5-number summary, you can actually make a box plot. That's not too bad either. So if you wanted to make a box plot, let's say we were going by tens. So 10, 20, 30, 40, 50, 60, 70, 80. So each of these are 10. I know this problem doesn't ask for it, but it's good for you all to see. So what do we do? Well, this 52 is the median, so we draw a big old bar right by the median. So right there, we'll say, is the median. That's 52. 35.5 is the quartile 1, and 63 is the quartile 3. So third quartile. So 35.5 will go down to here. Say that's about 35.5, and then 63 maybe right there. And you make a box. Okay. So then from there you have the the whiskers, or so for those of you, rather than call it a box plot, box and whisker diagram, or things like that, all kind of mean the same thing. Box and whisker plot. So now we got to extend down to 21. So we put a little whisker down here. Oh, don't let your eyes fool you. That's a straight line. So there's our whisker. And then we go all the way up to 79. So here's another whisker. So on and so forth. Okay. So what this means is actually from 63 to 79, you should have about 25% of your data values. From 21 to 35.5, you should have about 25% of your data values. Inside this box, right here, you're looking at about, in that case, about 50% of your data values, and so on and so forth. So it kind of tells you how to break down percentage-wise, even though it doesn't look to scale necessarily. So 50% of your values should be above 52, 50% should be below 52. I know that doesn't look to scale, but that's what happens with a box plot. Okay, so hopefully that kind of ties it in with the 5-number summary as well. Alright, so another question that I kind of seen popping up a few times is what's the difference between a frequency table, relative frequency table, cumulative frequency table, and cumulative relative frequency table? So we'll do all of them all at once and kind of hit that point home. So during the Olympics, the U.S. teams received either a gold medal, which we'll denote by G, silver medal, which we'll denote by S, bronze medal, which we'll denote by B, or no medal, which we'll denote by N. So after all the events were complete, the overall results for each team is listed below. So you have this B, S, S, N, 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 G, G, so on and so forth. Find a frequency table, relative frequency table, cumulative frequency table, and cumulative relative frequency table for the medals in the above data set. Okay, so with that in mind,
sorry, I don't know that one.
I guess my echo wanted to speak in there. So let's take a look here. I'll just make it one whole big table. Obviously the things we're searching for are gold first, and then usually silver, then bronze, and then we would go wah 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 for those people that got no medal, right? And as I said, I'm going to try and combine them all into one. So if you have a frequency table, oops, I think I put relative frequency. It doesn't matter which order technically you put them in, but then relative frequency, then cumulative frequency, and then finally cumulative relative frequency. Okay, so what's going on here? The frequency table. So you're just counting the number of times this occurs. So let's start with gold. Notice we have 2 right here for gold, so I'll box those off. And then that's 3, 4, 5, 6, 7 golds. And I believe that's all the golds. So we'll put 7 in our frequency table. Silvers. Okay, so we'll circle these. You got 2 silvers, another 2 silvers. So that makes 4 silvers overall. I don't think there's any others. Bronze. Let's see what happens here. And so we'll do triangles for bronze just so I can distinguish triangle. So there's 1 bronze, and then 2 more bronze, so that makes 3 bronze. And hopefully we'll end up with a nice number here to underline the rest. So 1, 2, 3 for N, 4, 5, 6. So, and notice that worked out pretty nicely. So 7, 4, 3, and 6. Now, in order for us to talk about relative frequency, you can write decimal or percentage. I recommend percentage. So what we'll need though is a total. And so our total here is, if you add up these numbers, you get 11, 14, 20. So our total is 20. That shouldn't necessarily appear in the frequency table, but in order to calculate a relative frequency, you're going to need that. So notice what we're having is you take 7 divided by 20. That's how you're going to figure out your relative frequency, because we want to turn that into a percentage. So this equals, if you basically multiply both by 5, that gives you 35 over 100. So that tells us we're at 0.35 or 35%. Okay, in a similar manner, we have 4 over 20. So that would equal 20%, right? And then you have 3 over 20, which equals 15%. And then you have 6 over 20, which would equal 30%. Now think about this. If we've done it correctly, and we haven't rounded, right? If we round, you can get some rounding error and things like that. We should get 100% after all said and done. So you get 55%, that's 60, 70%, 100%. And after you see all that, I'm just going to erase that so you can see them as percentages. And that's what we're looking at there for our relative frequency. You can also write them as a decimal too, by the way. And even the fraction bar isn't so bad. Now, relative, the way to think of that, percentages. So now, what does cumulative mean? Cumulative, you can think of as a sum. So we need some sum here. And what is the sum that we're doing? Well, we're doing the sum of the rows and above. So notice this is the only row in the first case, so you have 7. But so our next one we have 4. So what we do is we take 4 and the row above is 7, so we add those two together and we put 11. Okay. In our next case, we have the bronze. We have 3, and then the rows above it are 4 and 7, so we got to add 3 plus 4 plus 7. That should equal 14. And if we've done this correctly, when we add up the last row with the ones above it, we should end up with the total. And notice we do. We get 20 when we add 6 to that. So that's how we come up with our cumulative frequency table. So it's just a sum of the row and the rows above it. That's all there is to it. Okay? So now what is the cumulative relative frequency? So it's basically we're doing the cumulative frequency, and then we're taking those as a percentage every time. And by the way, if you notice, like the cumulative frequency, people ask, well, what could that tell us? Notice if we look at the bronze row, that tells us that the U.S. teams received 14 medals, right? So essentially we have a nice way to get the number of medals that the team has won. An easy table for that. So, and back to the cumulative relative frequency, remember the word relative means percent, the cumulative means a sum. So we want a sum and a percentage, right? So we're going to kind of add these up. Now to start, things start the same. We go 7 out of 20. In which we know that equals 35%. Okay, but in the second one, this is going to be a little bit different. We aren't going to be adding up all the percentages in this case to see that it equals 100%. What we're doing is we're taking the cumulative frequency row, right? So that 11 in that same row, and dividing it by the total. So this is 11 divided by 20. That's 55%. So what you could say at this point is 55% of the medals earned or placements earned were either gold or silver by the U.S. teams. And then after that you can go 14 divided by 20. And so what does that equal? That equals 70%. Right? And then you could do, the last one would be 20 over 20, which equals 100%. If you've done a cumulative relative frequency table right, you should finish with 100% every time. So notice what we could have said is, if you look at that our third row where we had the bronze, right, because you have only 3 types of medals, you could say 70% of the U.S. teams earned a medal. So it gives us information that way. Right? And that's all the tables. I mean, frequency, relative frequency, cumulative relative frequency. As long as you can distinguish all those, you're in good shape. So, let's move forward once again. Now we're moving on to body mass index and normal distributions and things like that. So, you have the body mass index indices, which we call BMI, of American men between the ages 30 and 50 are normally distributed with a mean of 26.2 and a standard deviation of 4.7. Now, we have this, several health professionals have declared that men with a BMI below 18.5 are considered underweight. What percentage of American men are underweight? The key to any normal distribution problem that we're going to deal with in here is, the first thing is to find a z-score. And what the heck is a z-score? Well, the z-score it stands for the z equals x minus mu divided by sigma. Okay, and so what is the sigma? That's our standard deviation. And this mu is our mean. And x stands for our observation. Okay? So when we have this, what's actually happening? What we're finding a z-score, what it's doing is it's standardizing this normal distribution. So we have basically a nice normal distribution we can calculate values on. So what's our observation in this case? Well, we have our observation is 18.5. So we will plug in the 18.5 here. Okay. Minus our mu. Well, what is our mu? It's normally distributed with a mean of 26.2 and a standard deviation of 4.7. So plugging that in, making sure we're careful to put the numerator in parentheses, 18.5 minus 26.2, have all that in parentheses and divide that by 4.7, and you get some number, and we're going to round to the hundreds place because that's where our z-score table actually rounds things, and we get this negative 1.64. Okay, so what does this mean? First off, in terms of a normal distribution, that's a bell curve, right? And so in the standard normal distribution, which is what the z-score is doing, you have all these little values, and right down smack dab in the middle is 0. And then you can go in these different layers, and you have something like -1 and +1. And if you've looked at the videos before, you probably saw that, oh hey, we know that approximately 68% or so appear between -1 and +1, and then you can go on to -2. Well, what we have is -1.64, so that's somewhere in this region. And now we want to look at the people with a BMI below that value. So what we'll do is we'll shade in our chart, and it kind of goes all these values below, and that gives us some form of a probability, essentially. And so in order for us to find this probability, we got to use this chart. And there's no need to fear. There's a chart here, and I'll pull it up in our class. And remember, our number was -1.64. So we have our chart. This is, you have a table and whatnot. Normal distribution table is what it's under, and it's in the normal distribution section. And so we wanted -1.64. So notice here is -1.6. Hopefully you can kind of see that going on right here with our on our left hand side. You have -1.6, and then we want to go to the 4. So where do we go? Well, we go on over from -1.6 is -1.60 is the first column, -1.61 is the second column, -1.62 is the third column, -1.63 is the fourth column, and then -1.64, you get a nice little value. And notice that value is 0.0505. Okay, so that happens to be our percentage, but it's written as a decimal. So we're going to have to do some conversion here. So we'll go back to that little table there, and 0.0505 is our answer. And so we'll bring that back up. And so we know that this is 0.0505. And so written as a percentage, what percentage of Americans are underweight? And so you move that, multiply that by 100, you get 5.05%. Okay, that's simple. Now there's one little caveat though. When we were doing that drawing there, it was, if you notice the drawing up above, it had a very similar looking thing where it had an area of a normal distribution and it was shaded to the left. That's going to change here in our second problem. So we have men with a BMI of 30 or greater are considered obese. What percentage of men are actually obese? So in this case, our observations switch. So if we go x minus mu divided by sigma, the mu and the sigma, so the mean and the standard deviations, stay the same. And remember, those are population means and population standard deviations. So that's assuming it's the whole population involved. So in this case, you get 30 minus 26.2 divided by 4.7. And so after all is said and done, what do we get? Well, we get, take your 30 minus 26.2 and divide that out by 4.7. We're going to get 0.81. Okay? And now we're ready to go to our normal distribution. Drawing. And so 0, remember, is right smack dab in the middle here. 1's kind of off in this corner, so 0.81 might be something like this. That's our z-score. Now, we want 30 or greater. So which direction would we go? If this is 0, notice that would be less than. We want greater than. So the greater than direction would be this other side that we're shading in. Okay, so now when we're going to look at our table, we got to be a little bit careful. But remember, it's 0.81 that we're looking at. We'll go back to our table on the class normal distribution sheet. So we're looking for 0.81. And when you look at this here, see how it's shaded to the left. But our scenario, we want to shade it to the right. So we're going to have to calculate this 0.81, and we're going to have some value to the left of that. And we'll work with that in a second. So first off, 0.81. Here's 0.8 if you look on this right-hand table. And then 0.80 is that first number, which is the 0.87. I think that's a 451. But then that doesn't matter as much as the 0.81 is 0.7910. Remember, that's this area to the left, essentially, in our normal distribution. So 0.7910 is our magical number of the area to the left. And so when we go back to our little sheet, we know that all this area in here is 0.7910, or remember, that is just 79.10%. But what's the total percentage of this whole thing? When you look at it, the total percentage has to be 100%, because all the observations altogether is 100%. So what happens at the end of the day? So our answer can be found by taking 100% minus the 79.1%. Why? Because that would be this amount in the shaded blue region. Okay, so what does that mean? Well, that means our final answer, when you subtract those two, if this was 80%, by the way, it'd be 20% would be your answer. But so since you have that extra 0.9 percentage points, we get 20.90, and that's our final percentage as to what goes on there. So hopefully that lets you see how all this stuff works. We got the normal distribution and all that stuff going on in there. And if you have any questions in the future, feel free to either post them in the discussions, and I'll start doing another YouTube live stream, or just ask me along the way in the class, and I'll be happy to answer them as they come in. Hopefully you found this useful, and I'll be answering your questions soon.